We have today we have the last lecture by Zvi, and we will learn about UV properties of supergravity.
Okay, so let's continue our discussion of three loops. So as for n equals 4 super Yang-Mills theory, these are the set of diagrams you need. And the idea is you write down the identities between the diagrams, the dual Jacobi identities. And in some cases, because there's missing diagrams, like the triangle, because we know at one loop there can't be a triangle, then what happens is the identity between the diagrams, in some cases, becomes a two-term identity, NA equals NB, so the numerators are related in this very simple way. So the notation I'm using is, if I don't write the argument, it's just the standard argument. 1, 2, 3, okay, we don't need 4 because of momentum conservation, 5, 6, 7. So that's all of these. And then what happens when you do the identities is the labels get all twisted up because you have to relabel so that the three diagrams have a uniform labeling. And then when you rewrite it back in terms of related to the original labels, then you get these types of arguments in here. So the idea now is we want to solve the system. So let's see how we're going to solve it. So the first thing is we need a starting point. So the first thing is where are we going to start? And then, as I mentioned last time, if you look at these equations and you follow them through, you'll see that diagram E would be the master. Every single diagram can be written in terms of diagram E just by following through these equations. So we only need to study one diagram, and from that one diagram we can get all the numerators. That's what these equations state. Okay, so where do we start? Well, maybe let's start at one loop. So remember last time I had an equation, 1, 2, 3, 4. There was L1 this way, L3 this way. And when we do the sum over states, what we got out of this was a very nice equation, minus IST A3 1, 2, 3, 4, and then divided by the propagators that are inside these two blobs here. So that was L1 minus P1 square and L3 minus P3 square. Now if you stare at this equation for a second, you realize something pretty awesome. See, I have a tree amplitude, and then tree amplitude sum over states. What do I get back? A tree amplitude depending only on the external legs. So maybe we should do it again. Like, we'll do it again. So why don't we, well, let me turn it on its side a little. So I'm going to do it again. Like so. And you say, oh, I can do this because the algebra I do for putting this together, I just do it again. And then let me do it again. Let me do it again this way. So these we'll call iterated two-particle cuts. And they're very simple because the algebra that we use to calculate these cuts, let's say even a three-loop cut, right? The algebra that we do is the same algebra we did over here. You just recycle the algebra. So this is a very simple calculation. To do three loops, you just copy one loop. And what you're pulling out from here would be all the terms where there's no where you're imposing these cut conditions. Now the answer for this, if you just do that, it shouldn't surprise you, is very simple. It basically says that the numerator for diagram E, see, this cut looks just like that diagram, is equal to STA tree NE, let me call it capital NE, so I'm just pulling out this factor, where this NE is equal to S L5 plus P4 squared, just as simple as that. But notice there's a cut condition. This is L5. We follow, I labeled it C5 over there. Then L5 squared is equal to 0. So I don't really know the numerator completely because there's some ambiguity. Okay? But let's take this as the starting point. Now, what's that ambiguity? Well, the ambiguity see, it can't be in any of these loops. It can't be in these loops here because these are boxes, so they can't have loop momentum. This loop here has loop momentum, so maybe I can add like an L5 square, or maybe L5 minus P1 square, this propagator, or this propagator. So immediately I can write down an ansatz for what this numerator is. So let's just write down that this NE is equal to, well, this starting point. So S L5 plus P4 squared. I can't, let me just move it. So the NE, so NE is equal to S L5 plus P4 squared plus alpha S plus beta T L5 squared plus gamma S plus delta T L5 minus P1 squared, and then plus alpha S plus beta T L5 minus P2 squared. So what I've done here, you'll notice that sorry, minus P1 minus P2. So what I've done here, you notice the same parameters here and here, is you'll notice that the diagram has a symmetry, right? You can flip it over, it's the same diagram. So what I'd like to do is maintain that symmetry. So that's why I set these two parameters, this pair of parameters, equal to each other. And in general, what I would like to do to simplify my life a little is I want some auxiliary constraints. So first thing is we want no triangles, no one loop. Triangles or bubbles anywhere, or bubbles. Well, that I've already done over there. What we want is diagram symmetry is respected. Now, in general, you don't have to do it, you don't have to impose this. It's just a dumb idea not to. So you'd like to do that. And then the third one is an extra constraint. If we have an n-gon, then we want n minus 4 powers of loop momentum in the numerator. Okay, now this one maybe is not completely obvious why I want this, but this is done by experience from lower loops. This seems like a good idea to do. And if one of these auxiliary constraints is too strong, you just discover that there's no solution to the cut equations. Okay? So there's no harm in imposing as tight as you can, and if it's too tight, you just release the constraint. Yeah?
L5 squared is no longer 0?
So L5, so in the final answer of what I want for the numerators, I want L5 squared not equal to 0. But when I calculated with the cuts, I had this ambiguity that the L5 squared was equal to 0, so I basically lose that information. So because of that, I am imposing this ansatz where essentially what this is doing is getting my maximal cut correct, but then cuts, but because I haven't worked out or I haven't included information from cases where this goes off shell, I need to put them in my ansatz. That's the idea. So I'm now going off shell on the internal lines. And the question is, what are these parameters? And one thing you can notice very quickly that's kind of awesome is there's only 4 parameters. It doesn't take very long to solve this. So first thing we can do is say, oh, look, I got a pentagon. See? Diagram E, there's a pentagon, 1 power of loop momentum. So I just look at this equation, I say, oh, I don't like those L5 squares. Let me get rid of them. Yeah?
Why don't you have like an A squared L5 squared?
Oh, a what?
A squared?
I couldn't hear. Sorry.
You have an A squared L5
it's just dimensional analysis. If I wrote down an S square, then I've run out of dimensions of writing down an L square. The thing has to have uniform dimensions.
Oh.
Yeah. I mean, I could write down an S square, but then I would mess up that cut.
Right.
Okay. So we say, oh, I shouldn't be writing here. So let me go over here. So no L5 square. So that gives me a simple equation. Gamma is equal to -1 minus 2. Wait, sorry. There's a small error in my note. What's that? Well, it's just, sorry, I just read it off from here. So I have alpha, it's just alpha, or 2 alpha. Gamma is 2 alpha. Okay, and then delta is equal to -2 beta. So then I solve for that, and that's, of course, very simple. Let me define tau ij is equal to 2 pi dot lj. And then when I impose that, I get that diagram E is equal to S tau 4 5 plus tau 1 5 plus alpha S plus beta T S plus tau 1 5 minus tau 2 5. Okay, so that's already pretty simple. Now I'm down to 2 parameters. So now what we do is we pick another diagram. Let's say we pick diagram J, and then we look over here. And then we can use that. We get, if you just plug it in, you're going to get Nj is equal to S 1 plus 2 alpha minus beta, tau 1 2 minus tau 2 5 plus beta S t minus u. Now let's look at this fellow. And you say, okay, you see there's a 5 here. So that thing has loop momentum in the numerator, but if you look over here, there's only boxes. Therefore, this coefficient has to be 0. So that gives you another equation. So now you're down to 1 parameter. So now you need another equation for that final parameter. Where do you get it from? Well, I'm not going to push this through the details of it, but diagram A is a happy guy because it has no powers of loop momentum in the numerator. It's only boxes. So you just look at the equation. You just push through the set of equations, and find out what diagram A is. let me just tell you what diagram A is. See, diagram A is NA is equal to S squared plus 1 plus 3 alpha, and then tau 16 minus tau 46 S minus, well, etc. And you're basically done because no powers of loop momentum are allowed, and there's a power of loop momentum. So then the final answer is this alpha is minus 1/3. And our final answer, just done this way, is that the numerator for diagram E is, this is our master, is S tau 45 plus tau 15, oops, minus 1/3 t minus s, s plus tau 15 minus tau 25. And then all others follow, all others from the Jacobi. But we aren't quite done yet. What we have to do is we have to check a spanning set of cuts. You have to make sure that all the cuts actually work. And let me just say that they do work if you go ahead and check them. A spanning set of cuts is actually very simple for this case. It's the maximal cuts and next to maximal cuts. And just based on checking all of those, which is quite a simple exercise, you can verify that this is the correct answer for n equals 4 super Yang-Mills at 3 loops. So you say, okay, that's very nice. I'm very amused by that. But of course, the real fun is not n equals 4 super Yang-Mills. The real fun is n equals 8 supergravity. Because n equals 8 supergravity, we don't have to do anything. We just need to write down that the numerator for n equals 8 supergravity for any diagram is equal to, well, STA tree. Let me put that back. This thing squared. And then we have the numerator for n equals 4 super Yang-Mills. And this for the corresponding diagram squared. And that's really cool. So this basic idea is how we did, say, 4 loops for in n equals 8 supergravity. Certainly the better way. We actually first did it by unitarity, but then this is a much better way of doing it. Now, the problem that we're really interested in is the 5-loop case. So let me just jump to that and tell you about that story. So this story here is really great, except there's a little if, which I snuck in right here. See, all of the story I told you, at the end, this has to be true. The cuts work. If the cuts don't work, well, then you have to go back to the drawing board. You have to go back to the assumptions. There were maybe some set of assumptions you had, because you're trying to solve these functional equations, which is actually very hard unless you make some assumptions. And after some effort, it turns out that the case of n equals 5 supergravity, n equals 8 supergravity, or at 5 loops is not so straightforward for reasons that we don't actually understand. So we're faced with a dilemma. On the one hand, you have to use double copy. because if you don't do double copy, you're not going to do that calculation. It's just completely out of the question. It's just the vertices are too complicated. On the other hand, this story I told you, it doesn't follow through straightforwardly. There's some kind of problem. So I'll explain what the trickery of how to get past that trouble is. So the basic thing maybe I want to emphasize is the way amplitudes works, the general field of amplitudes. What you do is, by some technique, you do some calculation of some quantity. Maybe it's a for loop, n equals 4, super Yang-Mills calculation, and then based on that calculation, you learn there's some kind of structure like this. This is actually how it was done. And then based on that structure, what you do is you learn how to do calculation. That's this endless cycle of calculation, which then leads to some kind of deeper understanding, and then the deeper understanding allows you to do other calculations. And that's a theme you're going to see throughout. Basically, anyone who's going to stand up here and say, oh, look at this beautiful structure, the place they got it from is there's some calculation which then teaches them about the structure. So I want to show you a structure at 5 loops, hot off the presses. Now, the general question that we're after is what's the UV behavior? So if you attack the problem kind of naively, you'll say, well, it's kind of obvious. It's going to be badly behaved at some loop order. And the argument for that is pretty simple. If you have a loop calculation, some kind of a loop diagram, and we're going to do it in Yang-Mills. The general structure, there's some propagators, there's some momentum up here that comes from a vertex. Let's say there's a 3 gluon vertex, let's say in Yang-Mills. Then we all know that this has 1 power of momentum, so there'd be 1 power of a loop momentum here. Now, if we look at gravity, then there's 2 powers of momentum. If you take 1 power and you turn it into 2 powers, then you get an integral that has a worse behavior. It's as simple as that. And based on that, then you can argue that gravity is going to be poorly behaved in the ultraviolet. And if you try applying supersymmetry, you realize pretty quickly supersymmetry itself does not have enough power to deal with this problem. As the loop order goes up someplace, you're going to get very high powers, and then people say non-renormalizable, untamed infinities. Okay, but let me ask you a question. How do you know this is really true? I mean, okay, you can say this. Arguments are cheap, but you know, the name of the game is that we actually know how the theory behaves. And of course, to know how the theory behaves, there's only one way to do it. You have to calculate the infinity. Arguments are generally not good enough because if there's a symmetry or a structure that you haven't understood, perhaps, let me just throw out the double copy structure. Maybe that hasn't been incorporated in the understanding of these ultraviolet divergences. So if there's some structure you haven't incorporated, then any kind of argument you have about how the theory behaves is not going to be complete. So you just want to calculate the damn thing and just, you know, end the arguments, just know exactly how it works. So there's the theory the best theory to be studying is n equals 8 supergravity. And that's because it has a lot of symmetry, a lot of structure. It's by far the tamest of the theories that, of the supergravity theories in the ultraviolet. And also it has simple equations behind it. I showed you simple cutting equations, so it's obviously the place that you like to really understand this. So there's a simple formula that we'd like to check. So n equals 4 super Yang-Mills has a formula for the critical dimension. By the critical dimension, I mean the dimension where the theory first diverges. So it's the lowest dimension where you get a divergence. And for n equals 4 super Yang-Mills, for L greater than 1, this has been checked explicitly, L less than or equal to 6, but it's very likely it's true in general for any number of loops. You might notice that this implies that n equals 4 super Yang-Mills is ultraviolet finite in 4 dimensions, because you're never going to hit 4 at any loop order. And what's remarkable is n equals 8 supergravity. It has the same formula through L less than or equal to 4. And there's been debate for quite a number of years about what the behavior is at 5 loops. That's the one we wanted to understand. And to add to the story, well, I'm not going to explain this in any detail, but there is a case where we know of cancellations, ultraviolet cancellations, which are to this day unexplained by any kind of standard symmetry argument based on either duality symmetries or supersymmetry, and that would be the case of n equals 5 supergravity at 4 loops. Now, the structure of this theory is a little bit complicated. In the double copy, one of the copies is very much like QCD, so that makes it a little bit complicated. So we would definitely like to be studying this in a simpler theory, but at least in this example, there are these extra cancellations which we named enhanced cancellations. And the question is, does this happen in the simpler theory of n equals 8 supergravity, and then can we understand what's going on? Okay, so how do you attack the problem? Well, the little glitch is we have never been able to find a solution to these dual Jacobi equations that's compatible with unitarity. So what do you do? So after thinking about it for a while, there's definitely one thing that's absolutely clear. You still need double copy. You still need to do that. So the answer is be happy and just proceed. Do the double copy. So what we're going to do with 5 loops is we're going to look at the dual Jacobi identities. Okay. So that's IJK. IJK. And we have a representation of the Yang-Mills where it doesn't hold. So what we do is we say, do it anyway. So we're going to just apply the double copy. We're going to make this replacement. Now what happens when this equation doesn't hold? You're not going to get the right answer. Right? You're not going to get n equals 8 supergravity by doing this for the 5 loop n equals 4 super Yang-Mills. But what you realize quickly is you get an approximation of the right answer, and in a very specific way. So what you do, first let's look at the maximal cuts. So there's the maximal cut. And you stare at that for a second and you say, but wait a second. Those 3 vertices, the 3-point amplitude of supergravity is directly the square of the Yang-Mills. So if I take the answer of the n equals 4 super Yang-Mills and I impose a maximal cut, and then I double copy that maximal cut, it's correct. So the double copy, let's call it the naive double copy. By naive, I mean I don't have this working. Has correct maximal cuts. So that's a good step. And then you think about it a little bit more, and you say, okay, what about a cut like this, the next to maximal cut? And remember that on the blackboard I showed you that at 4 points it works automatically. So in fact, this cut is correct. All the next to maximal cuts are correct. Okay? But then, of course, at some point, something's gonna go bad on you, of course. Let's go over to a next square maximal cut. So we'll just kind of lump everything together. So now we're at a next square maximal cut. And is there any reason that you might expect this to work, to be correct for the gravity case? And of course the answer is no. I mean, why should it? You know, it's out of arguments. And in fact, one can check it. It's just, it doesn't work. But then you can ask, what's the error? And what you realize very quickly is the error is isolated the error is isolated. So each cut of these next square maximal cuts, they're wrong. So the error in that cut is isolated to a contact term. So let me just draw this contact term. Oops. I draw it like this. Okay. So this is now a diagram, not a cut. And the idea is that all the non-local pieces where I explode this out, they're already correct because the next to maximal cuts and the maximal cuts sitting above this were correct. So the only error that you could have is very specific, is the contact term. So what you do is you calculate this cut using KLT, and then you compare it against the cut of this naive double copy, and then you find the error. And then you collect the error, you write it down. Okay? Now there's a little bit of a problem here because it turns out you have to do this about 80K times because you have to go through next square maximal cuts, next cube, next fourth, next fifth, next 6 maximal cuts. So it's still kind of daunting. So then what do? Well, there's a little secret of what you're supposed to do when you're faced with something like this. Every day, when you wake up in the morning, what you have to do is you have to say, today is the day that I will find the simplifying structure. That's the secret. And then one day, you're going to wake up and you're going to say, ha, it's obvious. And it's true, what happens is you could find a set of formulas for these missing pieces entirely in terms of Yang-Mills. Okay? So just to give you one simple example, so let's consider some cut. So this would now be the cut in n equals 8 supergravity. And what we're going to do is we're going to write down, this is now my naive double copy. So this is the propagators. This is props. This is, call it the naive double copy. So that's, I'm taking some Yang-Mills representation where these dual Jacobi identities aren't holding, and I just do it. Well, that cut is not going to be exactly right. It's going to have an error. Let's call the error E. And the question is there a simple formula for that? And the answer is there is. And after a while, it became pretty obvious what the error had to look like. The error is determined by the violation of this function. And then you may remember I said if one copy has this working, it doesn't matter if the second copy doesn't. So then you say, it's got to be quadratic. The error has to be quadratic in that. And in fact, for a cut that looks like this, so let's just draw out a 5-loop guy. Of course, I could be drawing it at 3 loops. It's the same story, but it's more fun to draw it at 5 loops. Say a cut that looks like this. So there's a 4-point tree here. So we'll call that a 4x4. So there's a 4-point, and what's that error? Well, the error is given by a simple formula, which I'll explain what these things are in just a second. So there's a set of labels. So, I mean, one thing is you need some good bookkeeping, so you need a set of labels. So these are propagators. Just write them as Ds. But then you have to have some set of labels inside this blob. There are 3 possible propagators. And then this twisted guy. So there's 3 possible denominators, so you need a label for that. Like which one of these 3 diagrams you're talking about. Then you need a label for the blob. And then if you're talking about more complicated cases, let's say this is a 5-point, you have to label which propagator inside your diagram. So you need some kind of bookkeeping to keep track of what's what. But the final formula is pretty simple, where this J is exactly one of these discrepancy functions defined in terms of the original naive double copy. So let's put some labels like this one's 1, 2, 3. So if I take these blobs, I stick it in there, I get 3 diagrams, stick it in there, there's 3 diagrams, so that's a total of 9 diagrams. I need some labels to keep track of it, so maybe I'll have labels for the numerators of those 9 diagrams. So this would be for the first blob. That's for the second. And then I define these J's. All right, let me define J, say I2. So there's like just a placeholder. That little thing is like a placeholder to say that this index is in the second position belonging to the second blob. I just define that to be I1 is equal to, from 1 to 3 of I1, I2, and then this is for the Yang-Mills. So the important thing is we captured what we want. The key to doing supergravity is that you rewrite the problem in terms of Yang-Mills, because Yang-Mills might be hard, but n equals 8 or any kind of supergravity, it's impossible. So, but once you have these formulas, see, this is the extra piece in n equals 8 supergravity written in terms of Yang-Mills. So I've got the double copy working. Okay, so now you do this. Okay. Use these formulas, and then you can march down the cuts and collect all the different pieces, and that gives you the integrand. So this is how the integrand is computed. It turns out as you go n to the 4th, n to the 5th, n to the 6th maximal cut, it turns out it's easier to do it straight from KLT, but you do it numerically. But anyway, this is one of the key tricks for pushing through the problem. And you're always using the double copy. So okay, now you have an integrand. And now what we need to do is extract out of it the ultraviolet divergence. And in what dimension do we want it? Well, it's that formula. See, it's the dc 6 over L plus 4. And so that's d equals 24/5. So how do you do that? Well, the technology for doing that is well understood in QCD. So let's apply QCD technology. So that's integration by parts, identities. And also the other thing that we want to do is you want to series expand excuse me?
You can explain that before, please, because the formula is done.
Yes, sorry, I didn't say it there. Yeah, sorry, this 26/5. So you want to check if this is true. If it's false, then you're actually looking at the lower one. Yeah, sorry about that. Well, this is based on supersymmetry arguments and string theory arguments. So the idea is you want to check below that. If this thing is finite, then that formula would then be the correct one, because the divergence wouldn't be there. It would be pushed up to that dimension. Yeah, thanks, Sarah. Sorry about that. Okay. Okay. Okay, so what we want to do is then series expand in small external momenta. Or large loop momenta. And then apply the IBP technology. I don't have quite enough time to explain that, but let me just write down one equation. So the idea is you write down an identity in dimensional regularization. Which looks like this. So you pick an integral, and then you write down a total derivative. There's an appropriate matrix here that has to be chosen wisely. And this, when you apply the derivative, you get a set of identities, a linear set of equations that you then have to solve. I have to say, you have to be pretty clever to choose the right thing. If you choose the wrong thing here, you're going to make a complete scramble of this problem, where you're going to mix up the ultraviolet singularities you're interested in with some infrared singularities that are completely spurious. And you don't want to do that. But anyway, you take this, generate a linear set of equations, and then you solve a linear set of equations for the set of all possible integrals that are you obtain from the series expansion. And then when you solve that system, you get what are called master integrals. The master integrals are for this problem of 24/5. So this is the master integrals in this problem of 24/5. Then that set of is just 8 of them. Now, if you're wondering, okay, how many integrals did you have to do? The answer is there are 141,592 integrals that you're actually interested in doing. It turns out that the system doesn't close unless you make it a little bit more complicated. And then there's 845,323 integrals that you have to do. And then when you solve that system, there's only 8 integrals that remain that we call the master integrals. Now, let me just write down the final answer. The final answer so this would be d equals 24/5. The ultraviolet, this is only valid for the ultraviolet. Okay, and there's the answer. Now, these integrals, if you inspect them, they're positive definite. There's a relative plus sign. So what that tells you that, in fact, there is a divergence in d equals 24/5. And what that says is that n equals 8, the punchline is n equals 8 supergravity has worse behavior. Compared to n equals 4 super Yang-Mills. That's the punchline. And in fact, from the symmetry arguments, the prediction is a d8 r to the 4th counter term. This is what the divergence looks like. There's a 1 over epsilon in front of that. There's the 1 over epsilon. Epsilon is 4 minus d over 2 in dimensional regularization. So in fact, there are no enhanced cancellations, no extra cancellations. So that's a bit disappointing. So after all that work, all that effort, in fact, you discover that there's no special magic in n equals 8 supergravity at 5 loops, at least as far as the ultraviolet is concerned, some kind of extra cancellation. So that's kind of disappointing. But we can start looking at it. You know, when life hands you lemons, what you have to do is make some lemonade. So you start looking at this. And what do you start noticing? Well, first thing you notice, something really remarkable. See these numbers? So I pulled out a 16. I did that because these numbers are symmetry factors of those diagrams. So that's kind of weird. So I say, oh, where did that come from? So what you then do is you walk over to a table, since you know, we know n equals 8 supergravity, 1, 2, 3, 4, 5 loops, and you look at all of it, and then you start noticing that the relative factors, these are relative factors. So I'm dropping the overall coefficient. We're just looking at the relative factors of these vacuum diagrams, which encode the ultraviolet divergence. So these are divergent in 24/5 dimension. And we can go down this list and we start noticing some patterns. Now, the first thing that, besides these symmetry factors, you might notice something else immediately. If you look here, and you compare that to the list of vacuum diagrams, you'll notice something pretty spectacular immediately. Only 2 of them contribute. Could we have predicted that ahead of time? And the answer is yes, a complete no-brainer. What you do, by the way, this is with an appropriate choice of master integrals. If you make bad choices, you're going to get very confused. So always you need to make good choices. Good choices are, what you do is you make all the other master integrals very clearly have triangles. 1, 2, 3. There's a triangle diagram here, no one-loop triangle. So it's just like that rule I told you for the amplitude, except now it's at the vacuum level. Now you'd say, okay, why didn't you know this ahead of time? And the answer is because there's about 1 million integration by parts identities in between. It's not obvious that all the shaking you're doing, the series expansion, the shaking, makes it so that the rules of amplitudes carry over to the rules of the vacuum diagram. So that's why we didn't know ahead of time that things would work like that. And in fact, you go through all of them and you say, look, triangle, triangle, triangle. And then you start looking a little bit more. And the last couple of minutes, that's what I want to show you, is in fact there's complete consistency every time you look at a subdiagram. So we can look at subdiagrams. I'm going to inspect the subdiagram. See, there's a 4-loop subdiagram in there. And I can go through all the subdiagrams and I can compare them to here. And I can try to just ask the simple question, is it consistent? Now, if these are amplitudes, ordinary amplitudes, well, you say, of course there's a consistency. That's just generalized unitarity. Right? So it's not completely obvious that this is going to work, but on the other hand, you know, this is what we should be doing for a living as amplitudes people. We do some complicated calculation, and then you look at the answers. Is there a structure? So is it true that the subdiagram is related to this one? And then all these subdiagrams, every time you look at a subdiagram, there's a relation, direct relation between them. Notice also these are living in different dimensions. So that might be another reason you may not think it's completely obvious. Of course, thinking about it that it's living in different dimensions is not the proper way to think about it. You should really be thinking about this at an integrand level, the integrand of these vacuum diagrams, and ask what is the leading behavior of each one, and is there a consistency among them? And in fact, there is complete consistency. So what are we going to do with that? Well, yes, I still have a couple minutes. Well, first thing, let's just talk about the consistency of it. So if you look at this diagram, and if you stare at it long enough, you'll recognize this is actually a cube. Every leg is like every other leg. So there's a complete symmetry. So if I look at a subdiagram, right, I extract the subdiagram, I can do it 12 different ways. There's 12 propagators. So when I look at the consistency, let me just sum over all the different for-loop subdiagrams in this 5-loop. And that just gives me immediately 12. And then like this. So the original diagram, it had a leg here. I remove the leg. It leaves a doubled propagator. That's what these dots are, doubled propagator. Right? So it leaves 12 of them. And then I can say, well, that's very nice. What about this one? So then we can do that one. And that one, the legs aren't all equal. In fact, there's 8 of them that then go into this combination. So when you go through all the different subdiagrams, the for-loop subdiagrams, you'll get 8 contributions like this, 4 like that. We just add it up, and that'll tell us that under the, looking at the for-loop subdiagrams of the 5-loop, and if you then include these combinatoric factors, then out pops exactly the result, the for-loop result, plus 1/2. And I'm sure we're going to be able to prove this, because something this simple can't be accidental. Okay, and in fact, all subdiagrams or consistency for all subdiagrams. Now, what are you going to do with this? So you say, okay, this is pretty nice, but what are you going to do with it? And the answer is pretty obvious. We're going to 7 loops. And the reason is because now we have a structure that we can exploit. Now, there's 2 basic ways you can try to do that. You can directly try to bootstrap. Basically, you try to reverse the arrow, and you try to go to higher loops. That involves some guesswork. Or what you do is you use this, because you now know a lot about what the answer is going to look like, you use this to, instead of trying to construct the entire integrand, you just construct the pieces of the integrand that you actually need to target certain integrals, vacuum integrals, that you expect to be there. And that is just absolutely enormous simplification. So I guess I should finish by saying 7 loops and beyond. Okay.
Questions? Yes.
So the fact that all masters are vacuum is directly from the approximation, right?
Series expansion, yeah. Yeah, and no one knows how to do the integrals directly. These are well beyond, I mean, for the integrand. No one knows how to do, if you're dealing with the integrand before the series expansion, no one would know how to do an integral like that. We knew ahead of time that we could do these integrals for a very simple reason. It's because the QCD beta function had been done at 5 loops. So if they could do it, then we could do exactly the same type of calculation of these vacuums, except, of course, they're in 4 dimensions. We're in funny dimensions.
I understand correctly that at least in a 3-level case, you get some new relations between diagrams, because really you have KLC allowing to
Yes.
calculate string amplitude. You have another way to calculate the string, the gravity amplitude, and these two ways should be equal, and therefore you have a new relation.
Yeah, so that's right. So let's say back at 3 loops where the duality was working, then the fastest way to do the computation is with the duality. But then to actually know if it's correct, we have to use, basically you have to do generalized unitarity to directly verify that the calculation is correct. In the generalized unitarity, we get the gravity amplitude using tree-level KLT. So there's 2 different ways that you can calculate, and it's of course very important that they agree.
Okay, more questions?
Do you think there might be a simpler representation of the 5-loop integrand with fewer j's than the one we have now?
Sorry, with fewer, I missed what you said. Fewer what? Fewer?
These jk's.
Error function.
Oh, yeah. Yeah, of course. Yeah.
How would you find it?
Well, what you do, we certainly tried doing that. One way that you can attack the problem is you start imposing the dual Jacobi identities as much as you can. And then you stop doing it when your system goes inconsistent. The more dual Jacobis that are working, the more numerators, the more contact terms that vanish. So you could attack this problem systematically. Of course, what we were really after was getting an answer. That was the absolute priority. So we could go back and try to do that. Of course, we greatly prefer to go to 6 loops. So
what kind of checks can you do to convince yourself that you didn't make an error somewhere in the
Oh, so actually, that's a very good question, but I think the convincing part is on the blackboard. So ahead of time, we didn't know these consistency relations, and we could say we haven't even proven the consistency relations between the higher loops and the lower loops. But when you see something like this, right, where like this little thing right here, you see something like this, then even if you're not absolutely sure where it came from, I think you can probably convince yourself that you did it correctly. And there are also other indications that the system was solved correctly, that there weren't errors. There's endless numbers of checks on the unitarity cuts. So we do unitarity cuts beyond the ones that are needed for the construction. And certainly at every single stage you have to go through and convince yourself. But the final answer to that is when you get an answer that makes a lot of sense, then, and you didn't use that information in your construction, then you probably did it correctly. So I'm very confident that we did it correctly. And I even can quantify how confident. I have a bet that I lost. And I am willing to admit that I lost the bet based on this consistency that we see here.
Okay, there are no more questions. Thanks, Zvi, again for the whole lecture series. The coffee is outside.
Oh.